Now let's start talking about something called generator action. Perhaps when you think about electricity, you might think about the plug in your home or apartment where you can, plug your laptop or fridge into, and electricity is what powers it. What about if I ask you the question, where does that electricity come from? There's a pretty good chance the term generator is going to come to mind. Electric generators, that's the world we live in, the electrical world we live in. The electricity that we utilize on a day-to-day basis is produced somewhere. And in many cases, generators are what's responsible for producing the electricity that we use on a day-to-day basis. So what exactly is generator action? Well, imagine that we've got a magnetic field, North Pole, South Pole, and what we're going to do, instead of just passing a conductor down through the magnetic field once, perpendicularly crossing all of the lines of flux in one smooth motion, instead we're going to define a central point of rotation, and we're going to take a conductor. All right, I'll draw the attempted three-dimensional version of a conductor. And what we're going to do is we're going to spin this conductor now circularly within this magnetic field. The neat thing about this is that the conductor will never actually leave the magnetic field. It's going to go through a number of positions, which we're going to label just like the hours on a clock, from 0 or 12 to 3, 6, 9, and back, and of course all the intermediary numbers in between there. Okay, so 1, 2, 3, so on and so forth. Hopefully you're familiar with what an analog clock looks like. Okay, what we're going to end up with is circular motion here. So around a central point of rotation, we'll have circular motion. What's interesting about this is that the conductor has to cross magnetic lines of flux in order for an induced EMF to occur. So before we go any further into generator action, I'm just going to erase some of this stuff, and I want to talk about the difference between a conductor crossing lines of flux and a conductor just simply moving within a magnetic field. So here's our magnetic field, North Pole, South Pole. If I take a conductor here and I swing it this way, completely parallel to the lines of flux, the induced EMF, when I do that, and I can actually move this conductor back and forth over and over and over again, I will never actually generate a voltage. I'll never induce an EMF, an electromotive force. Remember Faraday's law of induction? E delta phi divided by delta T. So what I need to be doing is crossing magnetic lines of flux. If I'm moving the conductor side to side within a magnetic field, I'm never actually going to cross lines of flux, which means that I will not have an induced EMF. So the only time that I will ever have a voltage induced across the length of my conductor is when I move the conductor perpendicular or at right angles to the lines of flux, so straight down. Now what do you suppose is going to be the case if I take a conductor and I move it on an angle through this magnetic field? What we need to do in that instance is we would actually need to break the motion, the velocity of that conductor into its rectangular components, the vertical component and the horizontal component, right? And so you're going to deal with some angle, some velocity. You're going to use trigonometry to solve for the unknown sides here, so that only the portion of this velocity that is completely perpendicular to the lines of flux is what's actually considered as your velocity, your vertical velocity here, through this magnetic field, because the vertical motion is the only motion that actually goes into generating an EMF. And by vertical, of course, in this instance, I just mean the motion that is perpendicularly crossing these lines of flux. Okay, so what happens when we take a conductor? I'll draw the first circuit the first figure that I had up here. Okay, lines of flux. When we take a conductor and we spin it in a circular motion around a central point of rotation, we have a whole bunch of segments where we have some horizontal motion and some vertical motion. And what we're going to do first of all is we're going to look at the best case and the worst case scenarios. So there's 4 positions on this drawing here where we're going to have sort of a best case and a worst case scenario. When we are at position 0, which we'll call this, okay, which is going to correspond to 12 o'clock on an analog clock dial, all of our motion is going to be, we call that V, all of our motion, our velocity, our angular velocity, is going to be completely parallel to the lines of flux, which means that at this exact position, at position 0, we will not have any induced voltage, okay? So over here on the right-hand side, what I've got is just simply a graph that's progressing in time in terms of position. So position 0 corresponds to the origin here. And on the vertical axis of this graph, what I'm going to draw is the induced voltage, E. Now you'll notice that this graph can go both positive and negative. So we're going to define one particular current direction into or out of the board as positive, and therefore the other will be negative. What's important to note is that at position 0, all of our motion is at right angles to our radius line there. Okay, all of our velocity is completely parallel to the lines of flux, which means that if we were to plot the voltage on this graph, at position 0, we'll have just a dot at the origin, which indicates that there is no induced voltage. Now imagine that this conductor is going to swing clockwise. Let's take a look. We'll ignore position 3. Here, down here, this is position 6 o'clock on the dial. All of our motion, since we're moving clockwise, at this position is again going to be completely parallel to the lines of flux, which means that at position 6, we're also going to have 0 volts induced. So I'm going to put another dot right at position 6 on that graph. And finally, if this chart actually goes from 0 all the way up to 11 and then back to 0. So we know that if we rotate from 0 through 6 back to 12, which is 0 again, we should see the same thing take place at position 0 one more time. So we have 3 dots on this graph now for position 0, 6, and 12, or 0 again, okay, where we will have absolutely 0 induced voltage at this particular time. Now let's start taking a look at position 3. Right, so of course on the clock we'd have 1, 2 in between, and then 3. We're just going to look at 3 because at position 3, all of our velocity is at right angles to the lines of flux. All of our motion is perpendicular to the lines of flux, which means that this is our sort of best case scenario. Now the question is, which direction is current moving into this conductor? Right, if we were to just draw the conductor as an open-ended circle, just like we've done before, are we going to put a dot or a little X on that conductor indicating current moving into, or rather in the same order, out of or into the board? Well, we of course have to use one of our arsenal of right-hand rules, in this case Fleming's right-hand rule. So what we're going to do, remember the pointer finger points in the direction of the magnetic field, so in this case it's north to south. The thumb points in the conductor's relative motion. Now I'm sitting at an awkward angle to be able to do this, so there we go. And finally, your middle finger is going to point in the direction that current is going to flow. So you can see that my middle finger is pointing out of the board. So that means that we're going to put a little dot here at position 3, indicating that current is flowing towards us in this particular instance. Okay, so right-hand rule tells us current is traveling out. So what we'll do is we'll just arbitrarily define current out as positive EMF. So what that means is at any point on the graph when current is traveling out of the board, we're going to draw that as a positive value up on the scale here. So here's positive, and then there would be negative down there. So what that means is that at position 3, which is the one we're talking about, all of our motion is perpendicular to the lines of flux. Therefore, we're going to have the highest possible EMF that we can get. So this is, let's just define this point here as the highest value that we can get out of the circuit. We don't have to put a number to it. We're just going to recognize that since all of our motion is perpendicular at this point to the lines of flux, that's the highest value we can get because we're now crossing with all of our motion completely perpendicular to the magnetic field. Now, as far as positive flow is concerned, you notice that we've got 0 here, our positive maximum here, and then 0 back at position number 6. What do you suppose is going to happen in between here? Well, we're actually going to have some variation between 0 and our positive maximum. Notice that from every point from position 0 to position 6, some of our motion, if not all of it, when we break it down into individual slices, there will always be a component of our motion that is downward. Might not be a large component, but at all points from 0 to 6, there will be a little bit of motion that is downward. What that means is that that downward motion, and Fleming's right-hand rule tells us that at all points to the right of this red dotted line, we will have current traveling out of the board or towards us. Okay? That means that at all points here, there's going to be a varying value, but current is going to flow out of the board. And I'm just going to draw it as sort of a rounded off hump. We'll talk about this a bit later. All right, so at all points, it might not be the same value, but it's always going to be above the line here, which means these numbers are always going to be positive. Now, what happens once we get beyond position number 6? We go from position number 6. As soon as we get past that, our motion is now in the upward direction, which means that our Fleming right-hand rule calculation has to change as far as the current direction is concerned. So pointer finger, now our thumb points in the conductor's relative motion, which means that our middle finger is now telling us that current from position 6 up through 12, the current is going to travel into the board. So since we define current out of the board as positive EMF, we're going to have to therefore draw the rest of the circuit below the line because current traveling into the board is a negative EMF. So the same phenomena is going to happen when we get to position number 9 here, 9 o'clock on the face. You'll notice that all of our motion, all of our velocity, is completely perpendicular to the magnetic lines of flux, which means that this is the best possible case that we can have. This is the largest EMF we can have in the opposite direction. That occurs at position number 9, and so I'll just put a dot down here, and this we're going to define as our negative maximum EMF. Okay? And you can see the same sort of trend is occurring here. From position 6 back to position 12, the entire time some of the motion is upward. Not always the same value, but some of it is always going to be upward. The part of the motion in both cases that is horizontal or parallel to the lines of flux, remember that does not go into the calculation of induced EMF. It has no effect whatsoever. So this side-to-side motion, if we were to break the circular spring up into its two horizontal and vertical components, the horizontal component means nothing. It's only the vertical component. So at position 9, all of the motion is upward, which means we have our positive maximum. In between here, we're always going to have some upward motion, which means that I'm just going to complete this chart indicating that we're always going to have some upward motion, so some negative EMF for the remainder of that swing from position 6 to position 12, back to the start basically. Now, hopefully, many of you are familiar with this shape. This is indeed sinusoidal, or what we call just a sine wave. This helps us out quite a bit. We're going to get into calculating mathematically why this is actually the case in our next topic here. But the point is, once our conductor has reached one full revolution, this is cyclic in nature, meaning that if we go through another full revolution, all we're going to do is see the same signal one more time. So this particular graph, as long as we keep rotating with continuous angular velocity, this graph would just continue on forever. So we would see a sine wave followed by another sine wave followed by another sine wave, and so on and so forth until we stop rotating that conductor through that magnetic field. So the point of this topic is simply the maximums and the minimums. So we have our minimums at position 0, 6, and 0, or 12, and our maximums at position 3 and position 9.